Welcome, children. I hope you must have been waiting for hydrochloric acid or HCl gas part 2 in the previous video, which was uploaded a few days back. That was HCl part 1. It dealt with the general information about HCl preparation, but here and properties and physical properties also were discussed in that. But herein we discussed the chemical properties of hydrochloric acid. Hydrochloric acid is a strong acid. That means it ionizes. It ionizes 90 to 99% in water. Ionizes. It is a polar covalent compound and it undergoes ionization in aqueous solution. So it ionizes. Hydrochloric acid is a solution of HCl gas in water. So it is made by dissolving HCl gas in water. It reacts with metals, salts, and other compounds as well, and we are going to see some of these reactions as your course suggests. It reacts with metals above hydrogen in the reactivity series to give metal chlorides and hydrogen. It reacts with salts other than sulfates, since sulfate is at the top of the reactivity series uh, among the radicals, and chlorine lies below it. So chlorine cannot displace sulfate from their salts. And this is the reason why HCl is not used for preparing sulfuric acid. Sulfuric acid is used for preparing HCl, but HCl is not used for preparing sulfuric acid. Reaction with metals is as follows. This is a general reaction. Any metal M reacts with HCl to form a salt. It's chloride MCl, MxClY, where X is the valency of Cl and Y is the valency of metal. Remember, X is the valency of chlorine, which is always 1, and Y is the valency of the metal. And hydrogen is evolved or displaced from HCl by metal. If it is above hydrogen in reactivity series. Sodium and potassium cause explosions when reacting with HCl. However, the other metals react, giving off hydrogen gas and the formation of their chlorides. So we never react sodium and potassium, including rubidium and cesium, for those who want a better knowledge, because they are highly reactive. They even explode in water, which is a neutral compound, whereas HCl, which is highly reactive, may cause a bigger explosion. So to avoid explosions, we never react sodium metal or potassium metal with hydrochloric acid. Their chlorides are made in some other ways, in an indirect manner. So the aluminium reaction is as follows. It gives aluminium chloride and hydrogen. Zinc displaces hydrogen from HCl, forming zinc chloride and hydrogen gas. And reacts slowly with HCl, forming iron chloride 2, FeCl2, not FeCl3, and releases hydrogen. So iron also displaces hydrogen from hydrochloric acid. Lead reacts imperceptibly with hydrochloric acid to give a white salt, lead chloride, which is precipitated. This is precipitation reaction. And once a white covering of lead chloride is formed on the lead metal, the reaction stops. So it does not proceed till the entire metal reacts, because a layer of lead chloride will protect the rest of the lead from reacting further. Reactions with metallic oxides. Metallic oxides are converted to their chlorides and water is formed alongside. So let's see the reactions. Sodium monoxide reacts with HCl to give NaCl and water. I haven't written 2, so we balance the equation by writing 2 here. Calcium oxide reacts with hydrochloric acid to give calcium chloride CaCl2 and H2O. This is already balanced. Similarly, zinc oxide reacts with hydrochloric acid giving zinc chloride and water. This is also balanced. And magnesium oxide reacts with hydrochloric acid giving magnesium chloride and water. And all these are clear solutions because these chlorides are soluble in water, whereas lead chloride shown here will not dissolve in water. This will make the solution light green. It will make it light green. Reaction with hydroxides and carbonates. With metal hydroxides, the reaction proceeds just as in the case of metallic oxides. And you can see sodium hydroxide reacts with HCl giving NaCl and H2O. Magnesium hydroxide reacts with HCl giving MgCl2 and 2H2O, and so on with aluminium hydroxide and lead hydroxide, which again is going to form a precipitate. Carbonates are decomposed by hydrochloric acid to give carbon dioxide and water alongside the metallic salt. So magnesium carbonate gives MgCl2, H2O and CO2. Sodium carbonate gives NaCl, H2O and CO2. Lead carbonate reacts with HCl to give PbCl2, which is again a precipitate, water and carbon dioxide. Reaction with sulfides. Sulfur dioxide is given off with the formation of chloride and water. So in these reactions where you will see sulfides and bisulfides, I have taken 2 sulfides, sodium sulfide and calcium sulfide, alongside magnesium sulfide and hydrogen sulfide of sodium and hydrogen sulfide of calcium. The reaction gives you a chloride, water and sulfur dioxide. Sulfur dioxide will will be evolved, and it's a gas, so it has to be shown with this sign. With sulfides, IDES, HCl forms chloride and H2S, which is hydrogen sulfide, a gas smelling of rotten eggs. So smells of rotten eggs. Smells of rotten eggs. And if smelled in large quantities, it is poisonous. So with calcium sulfide and so on with iron sulfide. This reaction is very special as it is made to occur in Kip's apparatus to supply hydrogen sulfide for cation testing, which will come later on in +2. So Hydrogen sulfide, it can be formed by any of these reactions, but this reaction is slow. This is a slow reaction giving H2S at a very normal speed, which can be controlled in a Kip's apparatus, and this H2S is used for analytical purposes. Reaction with MnO2, manganese dioxide, silver nitrate, and lead nitrate. Manganese dioxide, a black compound, it is a black compound, oxidizes hydrochloric acid to chlorine gas. So when concentrated hydrochloric acid is dropped on manganese dioxide in a flask, it gives you a brown precipitate of manganese chloride. Water is also formed, and chlorine, a greenish yellow gas, is evolved, which bleaches moist blue litmus to white color. The blue litmus, which is kept on the top of the test tube in which this reaction takes place, first turns to red and then is bleached white. This is a way of preparing chlorine from HCl acid. Now the precipitation reaction, this reaction and these two reactions are very important. Silver nitrate gives a white precipitate of silver chloride with hydrochloric acid, and nitric acid is formed. Lead nitrate, when reacted with hydrochloric acid, gives a white precipitate of lead chloride, and nitric acid is formed. The difference between the two reactions is that when the PPT or the mixture is boiled, the PPT does not dissolve in the case of silver nitrate, but PPT dissolves when the solution is boiled and reappears on cooling. This is the difference, and this is how lead nitrate is differentiated from silver nitrate. Also, and more appropriately, silver chloride is differentiated from lead chloride. Both are white salts. Both are white chlorides. Reaction with ammonia and preparation of hydrochloric acid. Ammonium hydroxide reacts with hydrochloric acid. I have written aqueous because if I write HCl, people would be confused as to whether gas is being used or the hydrochloric acid is being used. So in both cases, we have solution, and we get ammonium chloride, which dissolves in the solution as water is also produced. Whereas ammonia gas reacts with HCl to give ammonium chloride solid. Dense white fumes are formed when the two gases are made to come close to each other. This happens, and this tells us the nature of ammonia gas. Hydrochloric acid is an acid. Even in case of gas, HCl gas has acidic properties. So it reacts with ammonia, which is basic. So it tells us that ammonia is basic. Now, hydrochloric acid is prepared by dissolving HCl gas in water. HCl gas is highly soluble in water, so the apparatus is set especially to prevent back suction due to lowering of pressure in the flask where it is being produced. So this tube comes from the apparatus where the gas is being produced. So HCl comes here and it is directed to water. It is not allowed to escape. it is directed into this beaker containing water. As HCl is highly soluble in water, more HCl dissolves and a low pressure is created. And see the funnel arrangement. This is known as funnel arrangement. This is funnel arrangement. It is just slightly dipped inside the water surface. If I dip it too much inside, water will move up and it will flood the production apparatus. So when the water starts rising, there is a gap and the water comes back. So this arrangement, which is known as funnel arrangement, stops the back suction, preventing flooding of the production apparatus. This is the fountain experiment, which is done to show the high solubility of HCl gas in water. We take water in a trough and the arrangement is made like this. This is an inverted flask where HCl gas is stored, and we have a dropper containing water inserted through this cork into the flask. Blue litmus is mixed in water, so this becomes blue colored, and a little water is inserted into this flask by pressing this dropper. As water enters, HCl dissolves in it, creating low pressure, which sucks up water from here. And as this blue litmus, or the water with blue litmus, rises, as soon as it comes out of the jet, a red fountain is seen. And this proves the high solubility of HCl gas in water. We can do the fountain experiments, and we will do the fountain experiment with ammonia. When we study that, that is the next thing that is going to happen. We have seen that HCl gas can be used to prepare hydrogen, sulfur dioxide and carbon dioxide, yet it is never done. The reason is HCl is volatile. It is a volatile gas. The heat of the reaction makes HCl come out of the solution and mix with the products. So carbon dioxide, if it is produced, it will contain vapors of HCl. Hydrogen, if it is produced or prepared, it will have vapors of HCl. So HCl, though theoretically can eject hydrogen from hydrogen chloride or can give you hydrogen, but it is never used to prepare hydrogen because it will contain vapors of hydrogen chloride. So when tested, you will not only test hydrogen, but you will test HCl also. Suppose if you put a blue litmus over the mouth of the test tube containing hydrogen or jar containing hydrogen, it will turn red. The reason is HCl is present in that. So being highly volatile, HCl is never used to produce this gas. We use a safer acid, that is sulfuric acid. Thank you for watching this video. Do like, subscribe and comment on this. Your suggestions are most welcome. Thank you and have a nice day.